Okay, Assalamu alaikum. كيف حالكم? This will be your last lecture and we should finish the material. Remember we stopped uh, talking about the saline and sodic salt last time. So today we will start talking about their classification and reclamation. Saline soils traditionally been classified as those in which the ECE of the saturation extract is greater than 4 decisemen per meter and ESP less than 15%. So they are soils that are affected with salts, but not with sodium. So the salinity, electrical conductivity of the saturation extract, that's what the E is, the saturation extract, which we obtain from a saturated paste, is greater than 4 decisemen per meter, but the exchangeable sodium percentage less than 15%. The major problem with saline soils is the presence of soluble salts. So no problem of sodium, mostly saline or salt problem. Because exchangeable sodium is not a problem, saline soils are usually flocculated and water permeability is good. If you have high sodium on the exchangeable site, it will make the soil dispersed, it will destroy the structure of the soil, and so the soil permeability will become very poor. If you don't have that sodium problem, then we don't have that type of problem where we have dispersion. So we have flocculated, which means we have aggregates and the water permeability of the soil is good. Saline soils can be reclaimed. Reclaimed means we make them better, we remove their problem by leaching them with good quality, low electrolyte concentration water. So you leach down the salts because they are salts, they are soluble. So you just leach them down. But the important thing is to notice you have to leach them down with good quality water. You don't leach soils with saline water and you expect them to get better. So you have to have good quality, low salt water to leach these salts with. Sodic soils have an exchangeable sodium percentage greater than 15, and the electrical conductivity of the saturation extract is less than 4 decisemen per meter. And the lower limit of the saturation extract, SAR, sodium adsorption ratio, if you remember, is 13. Consequently, sodium is the major problem in these soils. That's why we call them sodic. It comes from problem of sodium, sodic. Sodic soils have pH between 8.5 and 10. Because we don't have the salt problem to suppress the pH, usually they have very high pH, very alkaline, 8.5, between 8.5 and 10. The high pH is due to the hydrolysis of the sodium carbonate. Of course, this is very soluble and it gives you 2 sodium plus carbonate. Carbonate hydrolyzes, it becomes HCO3 minus plus OH. So it releases all the time hydroxide ions. That's why we have the high pH. Historically, sodic soils were often called black alkali soils, which refers to the dispersion and dissolution of humic substances resulting in a dark color. So, you know that the organic matter doesn't dissolve in water, but if you have high pH, the alkalinity will dissolve the humic substances. And you remember, you always learn that if you have high organic matter in the soil, it becomes darker in color because of the color of the humic substances or humus. So if that humic substance or those humic substances dissolve in the higher pH, they become dispersed and they spread over the surface of the soil, so the soil looks black. But it's not black because it's good, no, because of the destruction of the organic matter in the high pH situation. So you have black alkali soils, they have high pH, the dark color from the dissolved humic substances, so that's not very good. So when that's an indication of poor situation, poor quality soil. Reclamation is affected by applying gypsum, calcium sulfate, 2H2O, or calcium chloride to remove the exchangeable sodium. Remember, every time I talk about sometimes the English words where you pay attention to how we use them, reclamation is effected, carried out. You do something. If you put it becomes a verb to affect something that's affected by so and so. But affected, that means we carry out this process by applying gypsum, which is calcium sulfate 2H2O. Remember, if you say gypsum, 2H2O is part of it, or calcium chloride. So it doesn't matter. The main thing, we have to have a source of calcium. So whether you use calcium sulfate or calcium chloride, we're interested in a source of calcium to replace the exchangeable sodium. So this will dissolve, this or this will dissolve, giving you calcium ions. The calcium ions will take the place of the sodium as on the exchangeable sites, and sodium will be out in salt solution, and then you can leach it out. The calcium exchanges with sodium, which is then leached out, which is then, that means sodium. After you exchange sodium with calcium, sodium will be in the salt solution, which is then leached out as soluble Na2SO4 or NaCl. Why did we say Na2SO4 or NaCl? Depending whether you use calcium chloride. If you use calcium chloride, then the result will be sodium chloride. If you use calcium sulfate, then you have sodium sulfate that will be leached out. Then the third type is the saline sodic soils. We have the two. We have salinity and sodicity. Saline sodic soils have an EC of the extract greater than 4. Of course, if you say saline, remember, we define saline with their salinity with the ECE greater than 4. So if we mention saline, it has to be, the electrical conductivity has to be greater than 4 dissiemen per meter. And because it also says sodic, so also the exchangeable sodium percentage is greater than 5. So it has the two problems. Thus, both soluble salts and exchangeable sodium are high in these soils. Since electrolyte concentration is high, the soil pH is usually less than 8.5. Remember, in the sodic soils, because we don't have salts to suppress the high pH, we had pH between 8.5 and 10 a while ago. We just said that. But because we have saline conditions here, we have high salts, they suppress the pH. So the pH of these salts is less than 8.5, and the soil is flocculated. So we don't have the problem of the dispersion of the sodic soils. If the soluble salts are leached out, usually sodium becomes an even greater problem, and the soil pH rises to greater than 8.5, and the soil can become dispersed. So you can't reclaim the soil but by leaching the salts. If you leach the salts, then it becomes a sodic soil because you cannot remove exchangeable sodium by leaching the salts. So if the soluble salts are leached out with water, sodium stays there and it becomes a problem. Then we don't have the suppression effect of the salts to lower the pH. The pH will start rising. It will become above 8.5. Sodium problem will be worse, and then the soil will be dispersed and the structure is destroyed. In saline sodic soils, reclamation involves the addition of good quality water to remove excess soluble salt and the use of calcium source, as we said earlier, calcium sulfate or calcium chloride. So first you add calcium sulfate or calcium chloride, so it will be there so that calcium will exchange the sodium, get it out of the exchangeable site, then you leach. Then you can correct the problem of these soils. Okay. Leaching, management of saline and sodic soils. The saline soils, leaching with adequate low salt water, we already said that. Drainage must be adequate. If you leach and you don't have very good drainage, then there will be a rise in the water table and the salts will not move down, so you didn't solve the problem. So when leaching, always you have to have good drainage. Salts must be leached below root zones. You don't add just a small amount of water and move them down a few centimeters and you say, well, I solved the problem. No, they have to be leached below the root zone so the plants will not be affected. Leaching requirement, and this I think you take it in other courses, but I just like always to summarize things for you in this chapter. So I'm sure you cover many of these things in other courses also, but it doesn't hurt to also repeat it. So the leaching requirement can be estimated as LR leaching requirement equals ECIW. ECIW is the EC of the irrigation water, the electrical conductivity of the irrigation water, over ECDW. ECW is the EC of the drainage water. So you measure the electrical conductivity of your irrigation water and the drainage water that comes out of the soil. You collect samples from it and you measure it and you see what's the salinity of that. You divide them both, so that will give you the leaching requirement. Leaching depends on several factors. We don't have to go a lot in these because, like I said, this is covered in some other courses, but we just cover in summary these things. Okay, this is just to explain a little bit more of what we have talked about. We already talked about, but you can see in this figure, I put it so you can see what's happening. Exchangeable sodium and or EC must be reduced. Exchangeable sodium is mostly exchanged with calcium using, remember we said either gypsum or calcium chloride. If you use gypsum in water dissolves and gives you calcium plus sulfate. So suppose you have, this is the exchangeable site, clay or any colloid in the soil. So it has sodium on it. Okay, if you add calcium, the calcium will take the place of the sodium. Remember we talked about the exchange reactions, charge for charge. Calcium carries 2 charges, so it will replace 2 sodiums. So this calcium was originally there, the magnesium was there. So now we have these 2 sodiums, okay? And so you have 2 sodiums come out, okay? And then the sodium that's in water, it will leach below the root zone using good quality water, okay? So this sodium here, it looks like it shouldn't be here because you look at this figure, this is just a mistake in the diagram because we have 2 sodium here. We replaced them here with 1 calcium and we have the original calcium here. We have the magnesium. So there should be no sodium here unless there was another sodium here. So, but don't worry about it. The main thing is for you to understand the principle and remember charge for charge, 2 sodium will be replaced by 1 calcium. This carries 2 positive charges. This is 1 and 1, 2 positive charges. So the calcium will replace 2 sodiums. Okay, I will talk about something that's probably not mentioned in your book. This is usually covered in fertility. but it's very important for you to understand that because I don't know if it's covered in your other courses. Salt tolerance of crops. Because why are we interested in salinity? We're agriculturists, we're interested in crops and in production. And so we need to know the effect of these salts on the plants. So we talk about salt tolerance of crops. How do we talk about that? Plants differ in their tolerance to salinity, how they tolerate, how they can survive under saline or salt problems. First, we talk about the differences between plants or among plants. The plant species, say, usually there are some plants that are very tolerant. They're more tolerant than others. So when we talk about barley and cotton, they have considerable tolerance. If you compare barley, say, to wheat, barley is much more tolerant to salt or to salinity than wheat. And cotton is also very tolerant. Of course, there are you can find tables and books and literature, but here just to give you examples, what do we mean by the differences in the plant species? And then within the plant species, even the varieties or cultivars may have different tolerance. Soybean varieties vary in chloride exclusion. Chloride exclusion, that means they have the ability to stop absorbing chloride even though it's around their roots. That's what's the ability of them to exclude it, not allow it to go in, so that way it will reduce the effect of that chloride on them. So even different varieties have different way of handling and dealing with salts. And then the plant stage of growth. Even if you have the same species, the same variety, the plant stage of growth is important. So old alfalfa, I don't know, probably you have heard of alfalfa in some of your courses. If you took any plant courses, it's similar to what we call in Arabic barsim. It's a legume, it's a fodder for animals. So alfalfa is more tolerant when it's older than when it's young. So that means you have to water more, reduce the salinity more when the plants are young. As they get older in stages, then they become more tolerant. Okay, how do we measure the expression? Remember, we use this term many times, how to express things, what are the units, how do we talk about it in a scientific way? Expression of plant tolerance to salinity. Yield, yield decrease with a given amount of soluble salts compared with yield under non-saline conditions. So if we have, say, two areas, two fields, okay, one of them does not have any salinity problem. So this is non-saline conditions. And then you have another field close by in the same area with salinity problem. So the one with non-saline, that will be our like normal yield. And then the one that has some salinity problem, we're gonna compare that yield with the yield which is under non-saline conditions. We will see that in a minute. Then there is a term we need to know. It's called the threshold. Thresholds are the minimum level, the salinity levels of the electrical conductivity of the saturated extract, above which salinity limits yields or growth. Just a while ago, we talked that different species and different varieties in different stages, they are affected with salinity. So each plant will have a certain level of salinity. After that salinity level, the yield will be affected. So that number, that electrical conductivity, what is that value we call the threshold? So the threshold, that means if the salinity was below that, no problem, the plant will not suffer. Probably the yield will be close to normal. If you reach that threshold or higher, then the yield will be affected. So that threshold also will change from one plant to another based on their tolerance. We said the tolerance, that's how we measure tolerance. What is the threshold? What is the minimum level above which the plant starts suffering? Interactions among plants, soil, water, and environment. So it's not only the salinity, there are also climatic and environmental problems that all have to play together: soil, water, and the environment, whether you have hot conditions, if you have a humidity, no humidity, other things. Okay, now how do we measure that change in the yield that we talked about? Remember, we said we compare yield in non-saline conditions to yield with saline conditions. Above the threshold, you have to be above that threshold, otherwise yield will not be affected. So above the threshold, the electrical conductivity of the saturation extract level, plant growth generally decreases linearly with increasing salinity. So when you have that threshold for that plant and the salinity got above that threshold, then the plant growth will start being affected. It generally decreases. Plant growth here, how do we measure it? We measure it by the yield for us. So it will start decreasing, and that decrease, luckily, is usually linear. That means it's like a straight line relationship with increasing salinity. The relative yield, Y, at any given electrical conductivity of the saturation extract level can be calculated for any crop from values in the literature. I will try, there is a table I used to give to my students, which is from a soil fertility book. I'll try to scan part of that and put for you on e-learning so that you can see what we're talking about, because I don't know if it's covered in your fertility courses or not. But I will try to put some of that table so you know where we're getting these numbers from. So Y is the relative yield at any given electrical conductivity of the soil. So Y equals 100, 100, remember, that's our optimal yield, which is under non-saline conditions from land that's not affected by, so we give it the value of 100. And remember, any salinity above the threshold will start decreasing the yield. So how much it decreases from that 100? Remember, 100 is in an area that's not affected by salinity, no problem of salinity. We consider it the optimal, the normal yield. So we give it the value of 100%. So Y is the value of the yield we are going to calculate compared to that 100 under the conditions we have, how much salinity we have. So Y equals 100 minus B, open parenthesis, EC of the saturated extract minus A. B is the percentage yield decrease per unit increase in EC of the saturated extract level above the threshold. Remember, we said the yield or the plant growth decreases linearly with increasing salinity. So how much the slope of that line will change with the crop. So that's why we need to know that B. That B is not fixed. Each plant will decrease in its yield based on its tolerance. So this B is variable, and this we can obtain from literature and from these tables I talked to you about. So B, you open parentheses, EC, that's the electrical conductivity of the soil you have. You try to find what is the yield in that soil, which has an electrical conductivity of a certain number. And A is the threshold level for that crop. Okay, the threshold for that crop. So this is simple. Y equals 100, the optimal yield, minus B, which is how much it decreases per unit of salinity for that crop. Remember, Never forget parentheses. If you write this times this, you make a mistake. B multiplied by the difference between the salinity that you measure and the threshold for that crop. This is fixed from value from tables. This is your land. You take a sample and measure its electrical conductivity. So you want to show how much yield I'm going to get compared to the normal, to the 100% in that condition or under that situation. So A is the threshold level for that crop, and EC is the given salinity level of your land that you're planting in. So we'll take two examples to see how we apply that. So if we take alfalfa, remember I told you that's like berseem, that's a forage crop, legume forage crop for animals. A, which is the threshold, equal to this semen or millimoles per centimeter or this semen per meter. So B is 7.3, the percent decrease per unit salinity increase. If EC of the saturated was 4, so our soil that we collected, we are going to grow alfalfa in a soil that has this electrical conductivity. The threshold for alfalfa is 2. How much it decreases per unit, the yield, how much the unit it decreases for alfalfa per unit increase of salinity, 7.3. So we put it in the equation. Y, how much yield we expect to get, equals 100% the normal yield, minus 7.3 the B, the percentage decrease per unit, and the unit, how we measure it, the actual salinity, you subtract from it the threshold. So how many units above the threshold you have. So the yield you're going to get for alfalfa under these conditions, 85.4% of the normal yield. Let's look at another example, peach. Okay, A, 3.2. Remember, A for alfalfa, 2. This one tolerates more salts. However, look at when the threshold is reached, peach is affected faster because B is 19. B here was 7.3. So the decrease, the percentage decrease for each increase of salinity unit is 19 for peach. So if we plant them in the same type of field, okay, the electrical conductivity, the saturation rate of the soil we have is 4 millimoles per centimeter. Okay, so we carry out the calculation the same way. Y equals 100 minus B, instead of 7.3 for alfalfa, we put the 19, 4, which is the same salinity for the field, minus 3.2, which is the threshold. The threshold for alfalfa was 2. For this one is 3.2, so you minus 3.2. Again, parentheses, you subtract first, then multiply by 9. So the yield we expect is 84.8%. So if we plant peaches in this type of soil, we expect the yield to be 84.8% of the normal yield without any salt problem. For alfalfa, it was 85.4. This will be the last slide. This is very interesting, how we talk about tolerance of plants, classification of crops, tolerance to salinity, so that you learn how we talk about it. If the plants are affected by low salinity, we say the plants are sensitive. They're very sensitive to salinity, which is logical, even for people. So they are sensitive for this. So that means any salinity will affect them. They are very sensitive to salinity. And then if they tolerate higher electrical conductivity, we say they are moderately sensitive. And then as the salinity goes higher, we change the way we talk about it. Here they are tolerating higher amount of salts and salt. So we say they are moderately tolerant. Remember, the ones that are affected by low salinity, we say they are sensitive plants. These are moderately sensitive. Then the plants that take higher, we say they are moderately tolerant. And then the one that really take much higher salt and they can survive in it and produce, we say they are tolerant. Remember, we were comparing, say, barley and cotton. We said they are good tolerant plants to salinity. And then you reach a point where if it gets too high, unsuitable for crops, you cannot keep on with higher and higher salinity. There will be a limit that no crops can survive. So this way we cover all the material. Best of luck for you. And this way we covered and finished our course.